Giorgio di Russo, who is talking about perturbation in horizonless geometries. Please.
Okay, good afternoon everybody, and I would like to thank the organizers for allowing me to speak here in this very nice workshop. And let me start. So, an outline, the motivation, as already said Francisco, is the topic is black hole and in general exotic compact object or fastball perturbation theory. Okay, and the aim is try to point out, try to individuate observables in order to distinguish between black holes from compact objects. Okay. And actually, we will study observables like quasi-normal modes, tidal low numbers, and amplification factors. In order to compute quasi-normal modes, we used a lot of techniques like WKB approximation, this lever method, the numerical integration, okay? And in order to give another viewpoint on all this topic, we also used this recently discovered connection between the quantum Seiberg-Witten curves and the black holes and fastballs perturbation theory. Okay, and I will use all these techniques in order to study topological stars. Okay, as Francisco already said, and actually I will discuss about the quasi-normal mode spectrum for scalar, vectorial, and tensorial perturbation in topological star geometry. Okay, I will also discuss on the scalar tidal deformation in topological star geometry, and I will also try to show how a charged scalar probe propagates in topological star background. Okay, and actually we have some work in progress. Okay, with Massimo Bianchi and Donato Bini, we are trying to compute this observable, the self force in the topological star geometry using the post-Newtonian expansion and the MST formalism. Okay. Okay, but probably this slide is not very useful because you probably have already seen it. And as Francisco said, I will focus especially on the last phase of the black hole merging. Okay, so the ring down phase. The ring down phase is characterized by the emission of gravitational wave, and the signal of gravitational waves is dominated by the quasi-normal modes. Okay. And okay, also this slide is very stupid, but only to fix some ideas. You know much better than me that black holes violate the information paradox, and the fastball program in the fastball program the classical black hole arises superposition of microstates, so smoothed horizonless geometries. Okay, and this proposal was very successful in order to describe the macrostate structure for extremal geometries, but there is a little bit effort to do in order to say something about the non-extremal case. Okay, and as I said before, the question is how much a black hole looks different from a fastball, an exotic compact object, and what we usually do in physics when you don't know the properties of an object. Okay, you send stuff on it, so for example particles or waves. Okay, so we study the scattering properties of this object. Okay. Okay, so this is the starting point of black hole perturbation theory. Here I will focus for the moment on the scalar wave equation. The scalar wave equation can be separated if you have enough isometries, okay? And at the end of the day, you are able to separate the Klein-Gordon equation in a radial equation and an angular equation, okay? And actually, you are always able to put both this equation in this Schrödinger-like form, as already said Francisco. Okay, and the relevant quantity, obviously, of this differential equation is this function Q, that is proportional to the effective potential. Okay, And the radial dynamic is always governed by confluent by Euler equation or confluent versions of the Euler equation. And actually here I'm showing a sort of dictionary between the various Euler equation with respect to some black hole solution or fastball solution. Okay. So this is for what concerns the radial dynamic. There are some subtleties for angular dynamic, because if your solution is spherically symmetric, for example Schwarzschild, the angular dynamic is governed simply by spherical harmonics, okay, which are confluent hypergeometric. Otherwise, if you have only the symmetry with respect an axis, for example in Kerr, okay, also the angular equation is a confluent Euler equation, okay, but I will be more precise on this aspect. Okay, what's the definition of quasi-normal modes? Quasi-normal modes is a resonant frequency, okay? It means that it is a complex number, okay? And probably the most important part of the quasi-normal mode is the imaginary part, okay? Because you know that this is the time dependence of the wave function, and the sign of the imaginary part is crucial, okay? Because if the imaginary part is positive, you have an exponential growth in time, okay? And I will refer to this case as a classical instability. But I will be more precise on this aspect. Otherwise, if omega is negative, you have an exponential decay in time, and I will refer to this case as a stability, a stable solution at the linearized level, obviously. Okay, and quasi-normal modes are defined in terms of precise boundary conditions, okay? And at infinity, you must impose that the wave is purely outgoing, okay? And if you are working on a black hole, you have to impose at the horizon that the wave is purely ingoing, okay? Otherwise, if you are working on a smooth solution, okay, you have to impose in the cap of the geometry. The cap of the geometry is the point where the geometry ends smoothly, okay? In this point, we have to impose regularity, okay? So the exponent, the Frobenius exponent is real, okay? And here, very briefly, I would like to say, to tell about a sort of numerical procedure in order to compute quasi-normal modes. Probably in literature, this method is called the shooting method. I don't know. So you have your differential equation, okay? You solve it imposing the correct boundary condition at the horizon, for example, okay? And you get a solution. So you have one solution with the correct boundary condition at the horizon, okay? Then you repeat the calculation, okay, by using the boundary condition at infinity. So you solve this problem numerically, for example, okay, and you have another solution. So in order to obtain a single solution, okay, a unique solution, okay, you have to impose the matching, okay, and in order to impose the matching, probably the better thing to do is to construct the Wronskian of the solution coming from these two differential problems, okay, and then try to see where are the zeros of the Wronskian, and that, yes. Lambda B? What is lambda B?
Lambda.
This lambda?
Yeah.
Smaller than 2.
Can it be smaller than 2? The reason that I'm asking is because in that case, either the first derivative or the second derivative of psi 0 will diverge, which seems bad.
Yeah, the important thing is that this lambda must be real and positive. Otherwise, if, for example, if lambda is -1, is not regular in R equal to R cap.
He was worried about lambda as a half.
Yes.
Yeah.
So if lambda is a half, for example, then
Yeah.
I take the first derivative of this psi 0, and I get infinite.
Yeah.
Then
You are saying that it must be bigger than 2.
I don't know if it's bigger. I would prefer it to be an integer. Then it would be. Then
No,
all
it's
of the
not an
derivatives-
integer, but I
Okay.
agree with you. It should be always positive. Yeah, because you are requiring a regularity of the wave function in this point. Actually, I don't think that you need also regularity of the derivatives.
So it's okay for you if the derivative blow up in the cup.
Yeah, I think there is no problem.
You probably have to have at least one derivative being good, because otherwise your energy will be infinite, or some kind of energy will be infinite.
In general, in our situation, this lambda is real and positive, but not an integer. And okay. It depends on the equation, yes.
The equations don't allow lambda positive, lambda integer is not going to be integer. So the only thing you need to check is that you take phi dot and you multiply with the GRR, and if it blows up or not. If it doesn't blow up, it's a good perturbation.
Ah, okay. Okay. Here I would like to show how it is possible to perform a WGB approximation. Okay, and actually this is the typical shape of an exotic compact object effective potential. So you have an internal minimum and an external maximum in the effective potential, and differently from a black hole, because because the effective potential of a black hole has only the unstable photosphere. So you have the unstable photosphere, and here also the stable photosphere, okay, or light ring. And actually, in WGB approximation, okay, you can say that there are two families of quasi-normal modes. One is localized around the unstable maximum. These modes usually in literature are called the prompt bring-down modes, and the other modes which are localized around the minimum usually are called metastable modes or long-lived modes, as Paolo Pani already said 3 days ago. Okay, so in order to perform WGB approximation on the maximum, a possibility is the following. The real part of the frequency is simply the frequency of the unstable photosphere, okay? While the imaginary part is proportional to this lambda, which is called the Lyapunov exponent, that describes the chaotic behavior of geodesics near the photosphere, and the imaginary part is quantized in terms of this integer n, which is called the Overton number in literature. Okay. For what concerns the modes which are localized in the minimum, a way that you should follow for computing the real part is try to solve numerically the Born-Sommerfeld quantization condition, okay? And in order to estimate the imaginary part, you can say that the imaginary part is proportional to the tunneling probability across this quantum mechanically forbidden region, okay? So across the photosphere, okay? Okay, then let me show this very powerful semi-analytical method used in the past for computing quasi-normal modes due to this guy, Lever. Okay, and actually I would like to apply it on a specific case. I will apply it on the confluent equation, which is relevant for Kerr-Newman, Schwarzschild, top star, etc. Okay. So the starting point, the confluent equation, as Francisco already said, has two regular singularities in my language in z equal to 0 and z equal to 1, and an irregular singularity at infinity. Okay, so in order to implement this method, you have to do an ansatz like this, where you impose that the wave at infinity is purely outgoing, okay, according to this sign that here I'm calling epsilon, okay. So you impose outgoing conditions at infinity. Then suppose that you have mapped your horizon or your cap in z equal to 0. You have to choose this Frobenius exponent in order to implement or ingoing boundary condition or regularity according to your gravity solution, okay. Then you plug this ansatz inside the differential equation. You obtain a recursion relation, okay. And now you have to choose this other exponent, lambda 1, in order to minimize the numbers, the number of coefficient in this recursion relation. And what is possible to show is that for confluent Euler equation, it is always possible to put your recurrence relation in a three-term recursion relation. Okay, so with 3 terms. Okay. And if you are able to do this, you can impose a sort of consistency condition for this recursion relation, which can be written in terms of this continuous fraction, involving only the coefficient of your recursion. Okay. So actually, you have an infinite number of these continuous fraction, okay, labeled with this integer n. You choose one of them, is not important, okay? And then this is, actually this is a very, very complicated equation that encodes the values of the quasi-normal mode frequencies, okay? So you can solve it numerically if you want. Okay, the story is quite simple if you have a three-term recursion relation, but actually in general the terms in the recursion could be bigger than 3. Okay. Here I would like to discuss the case with 4 terms in the recursion relation, because it's relevant for what I will say about the vectorial and gravitational perturbation in topological star geometries. Okay, so this is a 4-term recursion relation. Okay, and this can be rewritten trivially in a form of a matrix equation. Okay, like this. So now you have 2 possibilities. By brute force, you can compute the determinant of this matrix. You truncate this matrix at a certain level. You compute the determinant, okay? And then you numerically solve this equation. And the solution are the quasi-normal modes, okay? This method usually is not numerically very, very stable, okay? But probably the better thing to do is try to use the Gauss elimination method, okay? In order to obtain a recursion relation, so a matrix with only 3 terms on the diagonal, okay? And the transformation, the Gauss transformation that we have to do are the following, okay? Then you obtain a 3-term recursion relation, and again you can use the consistency equation of the 3 terms case, okay? So I mean the continuous fraction, okay? Okay, so in order to introduce the cyber-Witten techniques, let me very, very briefly explain what is the theoretical framework of this, okay? We are in the context of super Yang-Mills theory with 2 supersymmetries, okay, with the gauge group SU2, okay? The field content in the fields, okay, that are involved, there is also a scalar, okay, in the spectrum, and the scalar potential is this, okay, and as usual in supersymmetric theories, the scalar potential has some flat direction. Okay, so you can choose some configuration of the scalar field that do not cost any energy. Okay, A here is the vev of the Higgs field. Okay, then you can construct the gauge invariant Casimir, which is this U. Okay, And actually this quantity is invariant under the Weil group of SU2, which is zeta2, okay? That the remnant of the gauge symmetry is this transformation A that goes in minus A, okay? As Francisco already said, the relevant quantity is the prepotential, okay? Because in terms of the prepotential, you have an exact description of the low energy effective theory, okay? This is the power of this theory, okay? And actually, as it was shown a long time ago by Witten, okay, this theory can be also described in terms of bound state of branes, okay? In particular, the horizontal line are stacked over D4 branes. The external one are flavor D4 branes, okay? The internal one are the core D4 branes, and the vertical line are NS5 branes, okay? Okay, so you can describe in the previous pictorial viewpoint of this story, okay, you can describe the dynamic of your theory in terms of this elliptic curve, which is called, let me say, classical Seiberg-Witten curve, okay? And these parameters PL, PR, and P0 are respectively the position of the flavor D4 branes and the position of the color branes, okay? And actually you can solve this curve in terms of this variable y, and you can see that you have 4 branch points in the complex plane, so you have 2 branch cuts. So the topology of the complex plane with 2 branch cuts is the topology of the torus. So actually you can define the 2 inequivalent cycles, okay, of the torus, which are these 2, A and A dual, okay? And now let me talk about, let me say, the quantized version of this story, okay? As Francisco already said, you have to embed the classical curve in a non-commutative background, in the sense that now the variables that I called before x and y now are operators with a commutation relation, okay? In particular, the commutation relation x commutator with y is equal to h bar. So h bar in this viewpoint is a sort of is a fake. Okay, so I can put it to 1 in the sense this is the quantized version in the sense that the background is non-commutative. Okay, and the Seiberg-Witten curve becomes a differential equation. Okay, that you can put in canonical form, so psi second plus q psi equal to 0, and the q function is the following, okay? Is 2 means that in the Anani-Witten construction I have 2 insertions, mass insertion on the left and 2 on the right, okay? This is my language. So this is the meaning of 2, okay? And actually, this is the same Q potential that you should have for an Oin equation. So an equation with the 4 regular singular points. Okay, and actually, you can, starting by Oin equation, you can obtain all the confluences of the Oin equation by doing this what now I am calling the coupling limit. Okay, so I send the coupling, the gauge coupling to 0. One of the masses to infinity, but I keep fixed the product of the old coupling times the mass, and this product is the new coupling. Okay, so you obtain the confluent Oin equation relevant for Kerr-Newman, Schwarzschild, and topological star, etc. Reduced confluent Oin equation, which is important for other solidons, for example. Yes.
A few slides ago, can you say what is the shape of the Seiberg-Witten curve, the classical one?
The shape?
Yeah, what's the shape?
The topology is the topology of the torus, but the shape imagine that you have the complex plane, okay? You have the square root, okay? This polynomial is quartic, okay? So you have four roots, and then you can choose where you are putting your branch cuts. Okay, this is an equation in y and x. Actually, I don't know what's the plot in 3 dimensions of this curve.
And after this slide, you're describing the Seiberg-Witten curve quantum mechanically, or in this equation? What's the
Quantum mechanically, the relevant difference is that now the variable x and y are not simple variables but are operators. Okay, this is the only difference. Okay, this is the what in literature is called the Nekrasov-Shadashvili background or the omega background. Okay. Okay. So these are all the confluences of the Euler equation, okay? And let me just for 10 seconds stress my attention on these 2 cases. So doubly confluent Euler equation and doubly reduced doubly confluent Euler equation, or Mathieu, okay? Usually mathematicians call this equation Mathieu equation, okay? These 2 cases are relevant because they enjoy a particular symmetry that exchanges z with 1 over z, okay? In the sense that they exchanges the position of the horizon with radial infinity and keeping fixed a point. And actually for a black hole, the point which is keeping fixed is the locus of the unstable photosphere, and actually this is a symmetry called the Couch-Torrens symmetry, and actually it's a symmetry of extremal black holes like extremal Reiser Nostrum or D3 brains and bound state of D3 brains. Okay, but I will not talk about this now. Okay, so you remember the quantum version of the Seiberg-Witten curve, okay? This is the integrability condition of the Seiberg-Witten curve, okay? And actually, this continuous fraction can be is dependent only on A, the cycle A, okay, which is an holomorphic function in sense, okay. And actually, you can solve perturbatively this continuous fraction in order to find the modulus U, okay, with all the instantonic correction, okay. So a series expansion in the gauge coupling Q. You can invert this quantity perturbatively in Q, and then you can compute the quantum version of the A cycle, okay. Then you can use the famous quantum Mattoni relation, okay, this one. These are very old results of n equal to super Young-Mills, okay. And you can integrate the Mattoni relation in order to obtain the prepotential. This is called the Nekrasov-Shadashvili prepotential, which is composed by 3 terms: the so-called 3-level term, the 1-loop term, okay, that do not depend on the gauge coupling Q. And then you have the instantonic part, which is an expansion in the gauge coupling Q, okay? And actually, you can also define the dual cycle by taking a derivative of the Nekrasov-Shadashvili prepotential with respect to A. Yes? Yeah, this is very...
What is the significance of A equals h bar over 2?
Where
what's
A
happened?
equal h bar over 2, where?
Yeah, when A is h bar over 2, what happens in that case? In your equation for dF1 loop, dA? Yeah,
This
yeah,
one,
yeah,
okay,
yeah.
yes.
When I set A equals h bar over 2, I get that the denominator vanishes. I'm asking what happens in that case.
When h bar is going to 0.
No, you've got a bunch of poles in that thing.
What's the physics?
Sorry?
What's the
The physics of?
When the gamma function,
When the gamma function is
S
going
zero, gamma
so
zero.
when the argument of the gamma
Yeah.
is a negative integer, you mean?
Yeah, or zero.
Okay, this is relevant for what I'm going to say for tidal of numbers. Your question is very interesting actually, but I will be very more extensive when I will talk about the tidal of number. Okay, because actually tidal of number, as I will show, are simply a piece of the derivative with respect to A of the one loop prepotential. But I will show it. Okay. Okay, now all this machinery can be applied for quasi-normal modes purposes, okay? And actually this is the confluent Oin connection formula, okay? Suppose that you have mapped your horizon or your cap in z equal to 0, okay? And your infinity in z equal to infinity, okay? So this is the formula that connects 0 to infinity. Now, by imposing that at infinity you have only outgoing waves, this translates in imposing a quantization condition involving a dual, always a dual, and sometimes some shift of A, okay? And this quantity is quantized in terms of this integer that can be interpreted as the overtone number. Okay. Okay. So let me introduce topological star, even if I am not the expert, but the expert topological star is in this room. And okay, so topological star are solution of Einstein-Maxwell theory in 5 dimensions. Okay. And they are symmetric under this symmetry called the double Wick rotation, okay? And the solution has the metric, electric 3 form and the magnetic 2 form, the field strength, I mean, okay? And actually, if you send, the solution depends on 2 parameters, as Paolo already said 3 days ago, okay? And if you send this quantity RB to 0, you recover Schwarzschild, okay? Schwarzschild solution times an extra S1 circle, okay? And this solution is spherically symmetric, okay? So the relevant dynamic is the radial dynamic, okay? And this is the equation governing the radial dynamic. And this solution is interesting because according to the values of the 2 parameters RS and RB, you have both the behaviors. If RB is bigger than RS, you have a fastball-like solution, so a solution which is smooth and horizonless. If RS is bigger than RB, RS becomes an horizon, okay? So this solution is a black hole. And they will call it black string, okay, because it can be mapped to a black string. Okay, and actually this range of the parameters is good for having a smooth horizontal solution, okay? And RB smaller than 2RS means no Gregory-Laflamme stability, okay? But I will be very more precise in the next slides, okay? I will talk about this instability in this context, okay? So actually this is the map between the scalar perturbation of topological star, okay, and the relevant Seiberg-Witten curve, which is the curve with 1 mass insertion on the left and 2 mass insertion on the right, which is a confluent Oin equation, okay? And this is the dictionary, okay? Okay, and these are the plots of the effective potential, okay? This Py is the momentum along the y direction, okay? The extra y dimension, okay? And if you tune properly this momentum, okay, you have a potential which in general shows both the light rings, so the unstable light ring, okay, and also the stable light ring, but also the unstable light ring, okay. Otherwise, if you set this momentum to 0, you have a black hole-like effective potential. Okay, so as I already said when I was talking about the WKB approximation, we expect the existence of two families, two classes of quasi-normal modes. Okay, one localized around the maximum, the prompt ring-down modes, and another family localized around the minimum, the metastable. Okay, and actually, the only thing that I want to stress now is that the imaginary part of the metastable mode is hierarchically smaller with respect to the imaginary part of the prompt ring down. And as Paolo already showed 3 days ago, in terms of the time evolution, okay, this reflects on the fact that these modes behaves like equals, okay? So they present themselves in the late stage of the ring down, okay? Okay, so let me discuss, this is a work in progress, okay? We are working on the metric and gauge field perturbation of topological star with Francisco, Josif, and Francesco, okay? So this is a work in progress, and all the results are quite solid, but not completely fixed, okay? And okay, and you know that, oh sorry, there is a misprint here, okay. The problem is that the perturbation in magnetically charged background usually do not enjoy the separation between the even and the odd perturbations, okay? But in this case, this problem can be circumvented if we dualize the vector field. Okay, so we can do this, and actually we are interested in computing the linearized perturbation. There is another misprint here, sorry. The linear perturbation around this solution. Okay, so this is the ansatz where we already implemented the separation between the odd and the even perturbations. Okay. And actually, let me focus on some of this function of this perturbation. In particular, we focus on 3 of them: HT, HR, and CY. And actually, at the end of the day, if you are able to solve this equation, this differential equation, and you can put them in order to satisfy only 2 differential equations depending only on one wave function. Okay, so you can decouple. And actually, these are the 2 Q functions. Okay, and you can notice immediately that this is not a Noether equation. Okay, because you have an irregular you have a regular singularity in RS, another in RB, and another in R equal to 0. Okay, and at infinity you have an irregular singularity. So this is not a Noether equation. Okay, in general, this is an equation with 5 regular singularities where 2 points collide in order to form the irregular singularity at infinity. And so this means that our cybergrid techniques in this case are not cannot be implemented. Okay, and actually we tried to estimate the quasi-normal mode frequency by using the shooting method, so the numerical integration, and and using the lever method. Okay, and in this case the lever method has 4 terms in the recursion relation. Okay. Okay, the regime of interest are 2, as I already said. Okay, you have the black string, so when RS is bigger than RB and RS is an horizon. In fact, you can see that here I choose the Frobenius exponent in RS, which guarantees ingoing boundary conditions in the horizon, okay, and outgoing at infinity, obviously. The other case, the solidon or the fastball, okay, where RB is the cap of the geometry and is bigger than RS, okay, outgoing wave and regularity in RB, okay. So these are the lever ansatz. Okay, and actually this is the plot of the lever function. Okay, this is the plot of the lever function in the complex plane, and you can see that the imaginary part in this peculiar case, R plus means that I am studying the perturbation for topological star because RB is bigger than RS. Okay, this is the soliton. Okay, the fastball. I am studying the limit that when RB is going to 0 reproduces Regge-Wheeler equation with spin 2. Okay, so this is the meaning of R plus. Okay, so as you can see from this plot, quasi-Riemann modes have only negative imaginary part. So we have evidence for stability. Okay, so in this regime with these parameters, this solution is stable. And here I show some values of these modes, okay, with computed with the lever method and numerical integration, okay. Okay, let me briefly discuss about the Gregory-Laflamme instability. And Gregory-Laflamme instability is a classical instability that arises in the context of black strings and black branes in dimension bigger than 4. Okay, and also in this case we have evidence for stability, so negative imaginary part, okay, for both topological star and black strings, but in the gravitation in the Gregory-Laflamme stability domain. So when RB is smaller than 2RS and bigger than RS, and vice versa. So exchanging RS and RB for the black string. Okay. So we try to repeat the calculation that Gregory and Laflamme made when I was born, okay, but generalized it for topological star. So you have another parameter RB, okay. We are interested in this spherically symmetric perturbation, so the angular momentum is equal to 0, okay, and actually you can separate, you can decouple all the differential equation, and actually the only differential equation that you are going to solve is like this, okay, is a second order differential equation, okay, and it is not an equation, also this differential equation, because it has 3 regular singularities and another irregular singularity at infinity. Okay, so in this plot I show the first two are relevant for the topological star, because you see RB equal to 1, RS equal to 3/10, so RB is bigger than RS, so this is a topological star, but 2RS is smaller than 1, so we are outside the Gregory-Laflamme stability domain. In fact, we find an instability, so a mode with the positive imaginary part. Okay. In this other panel, you have RB equal to 1, RS equal to 8/10. So we are inside the stability domain, and in fact we find only stable modes. Okay, there are no modes with positive imaginary part. Okay. Now let me focus my attention on the black string. Let's see, RS is bigger than RB, because RS is 1, RB is 3/10, okay, also this case, so this is black string. And outside the stability domain, because 2RB is smaller than 1, okay, you have an unstable mode, with positive imaginary part. And inside the stability domain, you have only stable modes, okay. Okay, so now I will answer to your question, okay? And in literature, usually you will find information about static tidal lobe number. What it means? It means that people usually study the tidal deformation due to the presence of a wave that not depends on omega, on the frequency, okay? So they are focusing on the omega equal to 0 limit, okay? Because the definition of the tidal love number is well defined, okay? And actually, in order to introduce the dependence on the frequency of the wave, I'm using this CFT spiral definition provided by Francisco and Francesco and collaborators. Okay, and actually I will show quite in detail how to write down the love function. Okay, and in particular I will show how to apply it for a confluent equation. Again, because the confluent equation is relevant for topological scalar perturbation of topological stars. Okay, so this is the confluent equation or 1-2 Seiberg-Witten curve. Okay, in the decoupling limit. So when the gauge coupling Q has gone to 0. Okay, this equation is not annoying because it reduces to an hypergeometric equation. Okay. So this is the solution with the correct boundary condition, so ingoing or regular, okay? Then you analytically continue this solution at infinity, okay? And at infinity you have two behaviors, okay? In the dictionary you will always see that square root of u goes like L, the angular momentum L, okay? So you have this term which is increasing at infinity, and you have this other term which is decreasing at infinity, okay? And the tidal love number, as already Francisco showed, is the ratio between the term which is decreasing at infinity with respect to the term which is increasing at infinity, okay? So actually, this is the expression of the love number. Francisco showed how to compute the love function with the branching rules, fusion rules, but for me it's too difficult. I am very basic. These are only a sort of matching asymptotic expansion consideration, okay? And now this is the static love number, and in order to introduce the dependence on omega, you replace square root of u with the A cycle, with all the instantonic correction that you are able to compute with your computer. Okay, so in this way you introduce the dependence on omega. Okay, and actually, for example, this is the A cycle for scalar perturbation topological star. Okay, where I plug in the dictionary that I showed before. Okay, so this is an expansion in omega, okay, but the coupling Q is always proportional to the frequency omega, okay, so this is exactly the instantonic expansion. You plug this expansion inside the love function, okay, and you obtain a plot, okay, plot in the frequency. You can plot in the frequency, and you can see immediately that there are some poles. There are some poles in for some real values of omega, and actually me, Francisco, and Francesco, we tried to see why these resonances, this pole exist. Okay, and actually we found a sort of correspondence between the frequencies of the metastable modes, okay, and some of the resonances of the tidal love number. The blue line here is the plot of the Lever continuous fraction, the absolute value squared of the Lever continuous fraction. So the zeros of this function are exactly the frequency of the quasi-normal modes, okay. And here this yellow line is the plot of the argument of the gamma. Okay, this is the argument of the gamma, which is becoming a negative integer. So this is a pole in the gamma. Okay, so you have a lot of divergences in the tidal love number. Oh, sorry. 5 minuti. 10. 10. Okay. Okay, so there is a relation between all the metastable modes and the resonances. Okay, and the resonances. Okay, let me spend a few words on. This is a paper that we recently finished. Okay, we tried to study the propagation of charged probes in topological star background. The charged probes in this background are not particles, but are strings, because you remember in the solution there was an electric tree form, and the object that naturally coupled to electric tree form are strings, one-dimensional strings. Okay, and actually there is not a definition of how strings minimally couple to gravity. Okay, so this is our naive proposal, okay, of coupling. So this is the way that we use to couple this stringy probe to the topological star background. Okay, it is string inspired because you can see that this is a sort of mass shell condition for the strings. Okay, where mu is due to the oscillators of the string, and the other two contributions are coming from the Kaluza-Klein momentum and the winding number. In fact, in this viewpoint, the charge of your stringy probe is exactly the number of times that your string is wrapping around the y direction. Okay, this small q. And actually we studied both the regimes, so the top star regime, okay, and again we stated the stability, so we found only modes with negative imaginary part, and but we also studied the black hole regime, okay, and actually we studied the superradiance, the charge superradiance, okay, and this phenomenon is very visible if you look at the dictionary, okay. So, for example, in order to see this regime, let's perform the extremal limit. In the extremal limit, the coupling is going to 0. You have a divergence in the masses. But if you fix omega to be this one, this frequency is called the threshold frequency or the superradiant frequency, okay? You avoid the divergence and you have a very big simplification of the dictionary, okay? But you can further simplify the dictionary by asking that Q is very, very small, so the probe approximation.
Just a question on the previous slide. You said that there is no natural way to couple wound strings to the geometry.
No, in general, there is not a way to couple extended object minimally to.
This string is wound on the circle, spatial circle.
Yeah, the number of time the winding of this string.
You can couple it to your theory via the so-called Horowitz-Polchinski effective action. It's an action that allows you to incorporate the effect of the wound string. And include it in the back reaction. I can further discuss.
Yeah, we can talk about it because yeah. Okay. In these two limits, so near extremal and near superradiant, you can perform the matching asymptotic expansion of the solution at infinity and the solution at the horizon, and actually you can write down a sort of exact but approximate formula for the quasi-normal mode frequencies, okay? And you can see that this approximation is good if we are really in the near extremal case, because RS is fixed to 1, okay? So this is a good approximation in this regime, okay? Okay, then we also studied the amplification factor, okay? The amplification factor, as for the title of number, we computed it in the static case, and then we replaced the square root of u with a, okay? So the amplification factor is the ratio between the term which is the outgoing wave at infinity with respect to the term which is ingoing at infinity, okay? The square modulus minus 1, okay? Then you replace square root of u with a, and this is our exact formula for the amplification factor. And here I show the comparison between this red curve, which is the amplification factor obtained with the numerical integration, and here I show the comparison with this cyber-grid inspired formula with A computed with 0, 1, and 2 instantons. And unfortunately, the convergence of this series in Q is not very good, okay? Okay, very briefly, I would like to say this is a work in progress with Massimo Bianchi and Donato Bini. We are trying to study a proxy of gravitational waves by or from topological star, studying the massless scalar wave emission by a low mass, a neutral low mass, which is orbitating in a stable ISCO, so a stable innermost stable circular orbit around the topological star. Okay, and this formalism, the Manu Suzuki Takasugi or MST formalism, probably is the first time that is applied to a solution in 5 dimensions and with regular boundary conditions. Okay, so if R0 is the radius of your circular orbit, okay, these are the angular frequency and this is the relativistic gamma factor. Okay, the presence of this massive particle orbitating is perturbing our Klein-Gordon equation, okay, with this quantity. This quantity is the scalar source, okay. This means that in the homogeneous problem on the right-hand side has also a source term, okay, this one. So actually you can compute the particular solution with the standard green method, okay. And then you can reconstruct the full wave function with introducing the dependence on the angles, on y, on t, etc. And then the observable that we are trying to compute is the integral over time of phi computed on the radius of the circular orbit, which is called the self force. Okay. Actually, this quantity is in large L limit is singular, okay? Because when you are summing these quantities in L, you have divergences here, 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 and here, okay? So you have to regulate this quantity, okay? So you can subtract the divergent terms, and then you can add the pieces that you are losing, okay, by using the MST formalism. In particular, if you want to be precise to eta is 1 over c, so the post-Newtonian expansion, okay. If you want to be precise to eta to the 6th power, you have to add with the MST formalism L equal to 0, L equal to 1. If you want to be precise until eta to the 8, you have to add with MST formalism 0, 1, and 2, okay. Okay, I finish, and some outlook. The calculation of the topological self force probably can be generalized in 2 ways. Okay, the calculation can be repeated by studying not the scalar but the gravitational vectorial perturbation. Okay. And you can generalize from circular geodesic to hyperbolic or elliptic geodesic, okay? According to me, and from a more informatic point of view, if you want, it should be interesting to try to simulate the merging of two topological stars in order to study the gravitational wave signal, okay? And from a theoretical point of view, it should be also interesting to try to repeat the computation that we did for the quasi-normal spectrum of gravitational and vectorial perturbation topological star background by using the connection formula that Francisco showed. Okay, so using all the connection formulae for the differential equation with n bigger than 4 Fuchsian singularities. Okay. And try to match with the numerical result that we already have. Another project that we are following but is in an embryonic state is try to use an emittorial neural network in order to say something about the geodesic motion of non-separable geometries, okay? And try to localize the light rings, and when we know informations about the position of the light rings, we can say something about quasi-normal modes. And the final aim, but this is a long-standing project, our ambition is try to study the non-separable three-charge circular fastball by exploiting our previous result of obtained for the 101 superstratum, which is the near horizon geometry of three-charge circular fastball. Okay, so I finished.
Okay, thank you very much. So we had quite a few questions, but more questions? Right, so maybe I have one. So at a certain point you were making a distinction quite early between modes that have a large imaginary part and modes that have small imaginary part, depending whether they are perturbation around the unstable point or perturbation that are,
yes,
yeah, this one. So, so this the second type increases very rapidly, right? So from 10 to minus 14
yeah,
to order 1. The other one seems to increase less. So is there any difference? I mean, is there any reason for this difference?
These modes are for different values of the angular momentum.
Yeah.
And for fixed overtone number, so
okay.
n equal to 0. If you remember, in WKB approximation,
yes, yes. So the other one are for the same overtone. Is this?
The other one are for the same
for
overtone.
For different overtones.
For different overtones, and you
okay.
can see the growth here. So in this plot you see these are metastable because the growth is only in the real axis. Okay, and then you have a rapid growth also in the imaginary part.
So also the other one would increase if you did.
Yeah, sure. Yeah,
okay.
sure.
Okay.
And just a comment on this point. You see, if you just think about the quantum mechanics, these are, you have just a minimum. And if you count, you see that just doing quantum mechanics, you see that you have only three bound states. This is why you have just a few numbers.
Okay, so if there are no more questions, let's thank Giorgio again.
Thank you.